So welcome back, and so we're celebrating today the 61st Forman Symposium, um, and this course and symposium it's supported by the Isidore and Rose Forman Memorial Fund, and we're grateful to the Forman family. And here today, they've come to every single one of this. They probably know more about OBGYN than I do, and Dr. Adachi does. And they actually ask a lot of questions. Sometimes I don't know the answers. We'll have to read about it. But thank you again for joining us. And different times, huh? We were all masked up and vaccinated. So this fund that supports this activity was established in 1960, shortly after Dr. Forman's death on April 17th of that year at the age of 58. Dr. Forman was born in Russia in 1902. His father came to Philadelphia first, and in 1905, his wife and young Isidore Forman joined him. Dr. Forman graduated first in his class at Temple University School of Medicine in 1926, and you see some of the photos outside in the poster board. And actually, on the program, the back page shows his yearbook, medical school yearbook photo. So after graduation, he interned here at Temple, but back then it was called Samaritan Hospital. And when you walk up the steps on the Broad and Ontario, there's a stone that says Samaritan. And Samaritan Hospital was established by Russell Conwell, was the president of Temple University, to basically serve the poor of Philadelphia. And here we still are doing that. And people don't, people say, well, why Temple? And, Russell Conwell was a Baptist minister. And basically started teaching people from the community, from the neighborhood, about how to be preachers in his Baptist temple. And the Baptist temple is still there. It's not a temple anymore. It's for music and art and other activities, which says Baptist temple. And and then he decided to start a university for people that work. And Temple University Medical School was a night school. It was for people that will work during the day and will come in at night to study medicine. And eventually, it became, like many other schools, what they are today. So there was Samaritan Hospital, and Dr. Forman first worked under the direction of John Applegate, who was the first chair of obstetrics. Obstetrics was a separate department from GYN. And Dr. Applegate was a chair from 1901 to 1927. And then he was followed by Jesse Arnold, who was a chair from 1927 to 1941. And in that period of time, from 25 to 27, Wayne Babcock, who became the chief of surgery, was also the chief of GYN. And Dr. Forman worked with all these people. The department became one department. OB-GYN, OB and GYN joined in 1941. Dr. Forman's main interest was in infertility, which happens to be the topic that we're going to talk about today. And he had many writings in this field that brought him international recognition. One of Dr. Forman's books was co-authored by his chief, Dr. J. Robert Wilson. That's the namesake of my endowed chair. He was chair here from 1947 to 1963 before he decided to go to a cold weather climate up to Michigan. Not quite sure why he wanted to do that. At the time of his death, Dr. Forman was clinical professor of OBGYN and visiting chief to the Philadelphia General Hospital, PGH. And PGH, I think, closed like in 1975, 1977. PGH was the city hospital. It's what Temple eventually became. So PGH was the hospital run by the city and staffed by Penn, Jefferson, and Temple. So each major institution has its own service. Temple had an OB/GYN service, and Dr. Forman was the chief of that service at PGH. Dr. and Mrs. Forman married in 1932 and had 2 children, Paul and Miriam Forman, and Dr. Paul Forman is here with us today. Mrs. Rose Forman was the treasurer of the Women's Auxiliary of Temple Hospital. From 1950 to 1960, she was the office manager and receptionist in Dr. Forman's office. From 61 to 64, she was the director of volunteers at PGH. And in 1965, she became the executive director of Planned Parenthood of Southeastern Pennsylvania. So both of them were involved in OBGYN. Even after she retired from that position, she continued to work part-time in Planned Parenthood's education department. So again, here we are, pleased to be able to hold the 61st Forman Symposium and our 61st Forman lecturer. That happened also to be the 53rd Forman lecturer. Dr. Adachi had joined us before 8 years ago. So he's joining us from Rhode Island today. And I'll introduce him formally, like I mentioned this morning. So Dr. Adachi is an academic physician executive. He is the former Dean of Medicine and Biological Sciences at Brown University. He's a graduate of the Tel Aviv University School of Medicine and from the Harvard School of Public Health program in healthcare management.
Is there a number they can call? Because I usually have better luck catching her by email.
The magic of Zoom. I wish I could do that, mute people in some other circumstances. But I can only do it in Zoom. So he's a former president of the Society for Reproductive Endocrinologists, the Society of Gynecologic Investigation, the American Gynecological and Obstetrical Society. Dr. Adachi also served as examiner and director of the Division of Reproductive Endocrinology of the American Board of Obstetrics and Gynecology. Dr. Adachi completed residency training in OBGYN at Tufts University and fellowship training in the subspecialty of reproductive endocrinology at Johns Hopkins and at the University of California, San Diego. He held faculty positions at the University of Maryland, the University of Utah, and Brown University. Prior to joining Brown University, Dr. Adachi was the John A. Dixon Endowed Presidential Professor and Chair for the Department of Obstetrics and Gynecology at the University of Utah Health Sciences Center. And he was the founder and leader of the ovarian cancer program at the Huntsman Cancer Research Institute. He was elected to the National Academy of Medicine of the National Academy of Sciences in 1999. He's mentored to over 50 postdoctoral trainees and fellows. He's author or co-author of over 500 peer-reviewed publications, 120 book chapters or reviews in the general areas of reproduction, medicine, science, public health, law, bioethics, and human rights. He's editor or co-editor of 16 books. Dr. Adachi's work has also seen press with the New York Times, the Washington Post, the Boston Globe, the Huffington Post, and several other media venues. He has lectured nationally and internationally. Presently, Dr. Adachi is the chair of the Medical Executive Committee and the Medical Advisory Committee of the Jones Foundation for Reproductive Medicine, a member of the Advisory Council of the Hastings Center, and a member of the Board of Governors of the Tel Aviv University. A Franklin Fellow and Senior Advisor on Global Women's Health to the Secretary of State, Office of Global Women's Issues during the first term of the Obama administration. Dr. Adachi is a former member of the Board of Directors of Physicians for Human Rights and the Population Connection. Dr. Adachi is also a former member of the Council on Foreign Relations, the Global Agenda Council on Population Growth of the World Economic Forum, the Medicare Evidence Development and Coverage Advisory Committee of the Centers for Medicare and Medicaid Services, the Policy Working Group of the National Action Plan for the Prevention detection, and management of infertility of the U.S. Centers for Disease Control, and the Access to Care Task Force of the American Society for Reproductive Medicine. In addition, is the former advisor to the National Committee for Quality Assurance, the World Health Organization, the Rockefeller Foundation, and the Bill and Melinda Gates Foundation. So not quite sure how Dr. Adachi found time to be with us. So after that long introduction, Dr. Adachi, you only have 5 minutes left. Now, so Dr. Adachi sent the title of his talk, and he'll be able to share the slides. And we're all wondering how this is going to work. That basically we can have gametes being produced by just taking a few cells out of our mucosa, and the Formans here are wondering if we really need a man and a woman anymore, if we can just clone ourselves. So Dr. Adachi will give us the answer. I'm sure there's some bioethical issues associated with that. Well, thank you so much, Khalid, to be here with us.
So we will try to share now, right?
Yeah, please.
Okay. How is that working?
Yeah, yes, we see your slides. Good. Thanks.
Is that okay?
Yeah.
Okay. Well, thank you very much, Dr. Hernandez. It's a pleasure to visit with you all again. I enjoyed the morning session, which was very instructive in a number of ways. I will certainly retain a few of those lessons. So thank you for not just the opportunity, but also the education that comes along with it. As I think you alluded to earlier, there is a quote unquote scary element to all of this, the notion that one could secure a few cells from the buccal mucosa and through a series of transformation, convert them into gametes. And I don't disagree with that assessment, but like it or not, in all likelihood, this will transpire. Possibly not in our lifetime, but you could argue that it's all but inevitable. I say so with two more, perhaps, backup support facts. First, those of you who read the Science magazine, which is the leading scientific outlet in this country or really worldwide, chose in October of this year to dedicate a substantial spread to in vitro gametogenesis. That in itself tells you something about what this journal is thinking about the prospect of in vitro gametogenesis and the realization thereof. In addition, I can share with you that the National Academy of Medicine will conduct a workshop next year dedicated to this very topic, which I happen to be involved with, which could well evolve into a formal report, that is to say, a booklet, if you will, that summarizes all facets of this evolving field. The notion is to be, for once, ahead of perhaps the science journal that nails this phenomenon once and for all, or the New York Times op-ed that will appear inevitably at the same time. In a word, we're trying to be ahead of what seems inevitable, as opposed to playing catch up once it happens. I should point out that stem cell derived lineages are not limited to the germline. There are efforts underway to come up with amacrine neurons for the retina using stem cell derived technologies that may well start with a somatic cell. There is an ongoing effort to produce dopaminergic neurons for the striatum, particularly for patients with Parkinson's. There are efforts underway to develop trophoblastic precursors, motor neurons, and of course, gametes. The point being that gametes are by no means the sole target of this technology. There will be, in all likelihood, multiple applications for stem cell derived cell lineages. It's also useful to note that the Nuffield Council on Bioethics, which is the premier bioethics organization of the United Kingdom, in this document that is being projected, tries to foresee the subject matter that it will dedicate its energies to in the next, say, 5 to 10 years. And you may find it interesting to note that under the heading of human reproduction, the first subject matter that they propose to address is in vitro derived gametes, which yet again drives home the fact that the Nuffield Council as well considers this a highly likely outcome that may well be realized and therefore should be vetted from a bioethical point of view. They, of course, have other plans. They plan to discuss time limits on maintaining embryos in culture, womb replacements, preconception screening, whole genome sequencing of embryos and fetuses, genome editing of gametes and embryos, and egg freezing. In vitro gametogenesis, as you've already all surmised, is a disruptive technology. And the question is it achievable in the human? As we speak, that has not been accomplished, but it has been accomplished in the rodent, and we will be discussing that, of course, later. Whether or not the timeline is short or long, again, is uncertain, but the betting is on a relatively short timeline based on where the science stands today, and that may become more apparent later as we delve into the details. I find it useful to start the conversation along these lines by reminding us of Aldous Huxley and his 1932 book, Brave New World, because he too was obviously very preoccupied with the future of reproductive technology and made several key predictions. His view was that eggs will ultimately be produced via ex vivo ovarian cultures. He predicted that embryos will be created via in vitro fertilization, and that newborns will be delivered via ex vivo ectogenesis. In other words, will be carried for 9 months or thereabouts ex utero and then delivered rather than the conventional way. He was, of course, spot on with respect to embryos being created via in vitro fertilization. We know that to be a reality today. I suspect that his first prediction of ex vivo ovarian cultures is more likely to be realized in the form of in vitro gametogenesis, which we'll discuss today. Whether or not women will ever be relieved of the responsibility or the joy of carrying their infant is anybody's guess. Ectogenesis is still on the agenda. This last year has seen some significant progress in that arena, but we are probably still far off from this becoming feasible, not to mention the fact that significant consideration will have to be given as to whether or not it is desirable. So moving now to the topic of today, in vitro gametogenesis, I will one last time make reference to chapter 1 in Brave New World, wherein the director of the hatcheries and conditioning, as was referred to, makes note of the fact that 1 egg, etc., in the adult equals normality, and that making 96 human beings grow where only 1 grew before would mean real progress. Now, for the longest of time, the notion of in vitro gametogenesis was considered infeasible, and that was because of a prevailing hypothesis known as the soma germline barrier hypothesis, which was formulated by August Weismann, professor of zoology at the University of Freiburg, who in his 1893 book, The Germplasm, A Theory of Heredity, suggested that the germline does, of course, gives rise to the soma, which is immortal, you might say, but that the soma never gives rise to the germline, which means that it is mortal. It is that part of the hypothesis which was later disproven and made way for the possibility of in vitro gametogenesis. And the way it was disproven is really through the technology of somatic nuclear reprogramming, according to which you start off with a differentiated somatic cell. You convert it to a so-called pluripotent stem cell, a transition we will discuss, and then guide the pluripotent stem cell towards a gametogenic fate. All of this is based initially on a technology known as somatic cell nuclear transfer, which was invented, if you will, in 1958 by John Garden from Cambridge University, who published a seminal paper in Nature titled Sexually Mature Individuals of Xenopus laevis from the Transplantation of Single Somatic Nuclei. Specifically, a somatic karyoplast was combined with an oocytic cytoplast to give rise to a zygote, if you wish to refer to it as such, which was allowed to develop into a blastocyst from which embryonic stem cells were derived. This was the first technique which became available to convert somatic cells to embryonic stem cells that have the plasticity to morph into any one of the cell types. However, in 2006, a new technology known as induction came to the fore, thanks to the efforts of Shinya Yamanaka from Kyoto University, who published a key paper in Cell titled Induction of Pluripotent Stem Cells from Mouse Embryonic and Adult Fibroblast Cultures by Defined Factors. The plan here was to take a somatic cell, transfect it with a series of transcription factors, which would essentially reprogram that somatic cell into what is known as an induced pluripotent stem cell. Both technologies were eventually recognized by the Nobel Prize in Physiology and Medicine for all the obvious reasons, because they transformed science as we knew it, and more importantly, they stand to, if they haven't already, transform medicine as we knew it. And in vitro gametogenesis, as we indicated earlier, is just one facet of a large field that derives from these seminal developments. In other words, you can start with a somatic cell, convert it to either an embryonic or induced pluripotent stem cell, and guide it towards a gametogenic fate. What would be the prerequisites for this type of dramatic transformation to transpire? Well, you'd have to know the spec or the specs of the pathway. What cues does the induced pluripotent stem cell need to transform into a gamete? What would be the sequence of the cues? How would they be applied in whatever order? What would be the timing of the cues as they are being applied? And would there be a role for the niche in which the cell in question resides? For example, an egg, of course, resides within a follicle, and there is a significant role for the granulosa cells and the theca cells, which send certain cues to the oocyte and allow it to reach the stage of development it must. And the same would be true of the sperm, which in the testes are surrounded by the Sertoli cells and are being primed that way as well. The beginning of this field can probably be traced to 2003, when Science published a paper first authored or senior authored by Hans Scholler, then at the University of Pennsylvania, but now with the Max Planck Institute for Molecular Biomedicine. He was able to derive oocytes from mouse embryonic stem cells, an image of which is shown at the right lower hand corner of this slide. This was very early on, not much was known, but it was an intriguing clue. That same year, Toshiaki Noche from Japan reported that embryonic stem cells can form germ cells in vitro on the pages of the Proceedings of the National Academy of Science. And not too long after that, George Daly from Harvard Medical School reported on the pages of Nature more of the same, and René Reho-Pera reported more of the same in Human Molecular Genetics. And so back in 2003 and 2004, the notion that this could in fact become a reality began to take hold. The decade between 2000 and 2010 saw many papers that characterized the germ cell specification pathway in the rodent in some of the best journals, and this is just a sampling. Whereas the next decade, from 2010 to 2020, saw a plethora of papers on germ cell specification in the human, again, in leading journals. And so as we survey this state of the art in 2015, we can say that the germ cell specification pathway turned out to be not conserved between the rodent and the human, which poses, of course, challenges and is probably behind the fact that we are not there yet. And it also indicated that the genetic networks involved are quite distinct as well. In other words, even though we can make this now happen, as you will see, in the rodent, we are not able to yet claim the same in the human, in all likelihood because the two species are quite distinct in terms of the requirements for in vitro gametogenesis. We can think of it this way. We, in 2015, were in a position to take embryonic stem cells and induced pluripotent stem cells to what is referred to as primordial germ cell-like cells. But we weren't able to derive in the human haploid postmeiotic mature gametes, which is the endpoint. In other words, we were able to recapitulate the extragonadal component of the process, but had yet to traverse the intragonadal component of the process. Which means that the final frontier in the human, in vitro gametogenesis all the way, had yet to be accomplished and still has yet to be accomplished as we speak today. In the rodent, on the other hand, the cycle has been closed, meaning it has now been possible, as this Nature paper title suggests, to reconstitute in vitro the entire cycle of the mouse female germline. The leading author of this seminal 2016 paper is Katsuhiko Hayashi from Kyushu University, who began this experiment with either embryonic stem cells or induced pluripotent stem cells that were converted by him to primordial germ cell-like cells that were then combined with gonadal somatic cell to create a quasi-ovary, leading that to proceed to primary oocytes, M2 oocytes that are illustrated on the left-hand side of this slide, which upon fertilization gave rise to embryos which matured to blastocysts, and which upon implantation into surrogate mice gave rise to pups. In a word, starting with a somatic cell that was converted into embryonic stem cell or induced pluripotent stem cells, Professor Hayashi was able to take the process all the way to living pups. In the human, as we've indicated now several times, we're not quite there yet. Nevertheless, in 2018, on the pages of Science, Professor Mitinori Saito from Kyoto University reported on the generation of human oogonia from induced pluripotent stem cells in vitro. In this case, the starting material was human primordial germ cell-like cells, which were combined with xenogeneic ovarian somatic cells because it didn't have the appropriate human cells. Nevertheless, that gave rise to human oogonia, but not M2 oocytes, which would have been the endpoint. In other words, in the human, we have yet to take the process all the way to mature gametes, in this case, female gametes, but the same will eventually apply, of course, to male gametes. The missing links for what I describe here as terminal human gametogenesis is really the knowledge of the entire specification pathway and the ability to generate gonadosomatic cells which would simulate the niche which I referred to earlier. And we also have to remember that for this to be meaningful and useful, it would have to faithfully replicate all the steps of meiosis, for which certain gold standards exist as described by a group of investigators from the Jackson Laboratory now almost 7 years ago on the pages of Cell, according to which legitimate, if you will, M2 oocytes or mature sperm would have to display the correct nuclear DNA content, would obviously have to display the normal chromosome content and the organization thereof, and would have to display appropriate synapses and recombination if they are to successfully conclude their task. And of course, the ultimate proof is the generation of viable euploid offspring. It is these gold standards that would have to be met if in vitro gametogenesis in the human is ever to enter the clinical arena. At this point, perhaps it might be useful to discuss the scientific and translational process of this technology should it materialize. In terms of advancing science, this technology will give one an inexhaustible supply of germ cells. It would allow us to do functional studies otherwise infeasible today. It would allow the study of germ somatic cell interactions about which we still don't know a whole lot. And from a clinical point of view, it could reverse germ cell failure. For example, it would provide autologous gamete replacements in individuals who are unable to produce gametes for one reason or another, be it Turner syndrome or individuals whose gamete complement has been destroyed through one intervention or another. It would allow gene-edited gamete replacement in case of heritable diseases, mostly monogenic diseases. And it could even come in handy in the so-called mitochondrial replacement technology, which is a novel technology for the correction of mitochondrial DNA diseases. The impact of IVG on IVF, as we know it, is likely to be transformative. For one, it will eliminate the need in hormonal stimulation and in egg retrieval, which is a big piece of the IVF process. It might do away with gamete donation, with oocyte banks and the like, perhaps with the exception of age-dependent indications. And best we can predict, it will convert IVF to a laboratory procedure, which will affect the hundreds of IVF clinics out there, which are currently employing, of course, thousands of individuals and who, at this point, are very much in the in vivo mode. One would still require endometrial preparation and embryo transfer, but IVF as we know it will change dramatically. Whether or not affordability and access will be improved as a result of these developments is uncertain. I think we've all been there before, and the promise, even though theoretical, does not always materialize. There will be regulatory questions. This cannot be taken to the clinic absent clearance by the FDA. This is very much FDA jurisdiction. It will likely be evaluated by its Center for Biologics Evaluation and Research. It tends to categorize gametes produced this way as HCT-Ps, or human cells, tissues, and products. And absent their blessing, this technology cannot enter the clinic. And so it's not going to be good enough to accomplish the scientific feat of producing human gametes from a somatic cell. One would have to negotiate the FDA gauntlet before the technology can enter the clinic. And there are, of course, ethical considerations, as Dr. Hernandez already alluded to. On the one hand, this is a technology that can do a lot of good, which is why I refer to it as technology that might, in fact, bring along conventional Hippocratic beneficence, what we do every day, presumably. It could really address the issue of infertility in circumstances that presently are unaddressable. On the other hand, it will commodify reproduction in a manner that has never been experienced before. We all felt at one point that IVF was a market, obviously, change that commodified reproduction to a degree, but this will take it to a whole new level. It will raise new questions about the very notions of parenthood, which we don't have time to discuss in detail, but I think you can imagine. And there's always the fear that a technology such as this will get into the muddy area of human enhancement, which normally involves genetic engineering, but in this case may involve in vitro derived gametes. All of these issues doubtlessly will have to be carefully dissected. There are already papers being written on the subject, and so in addition to the regulatory paradigm, which we mentioned would have to be negotiated, there'll have to be a sense that this is an ethical proposition that we as a people can live with. Yet another element of the ethics of it all is the magnitude of the phenomenon. I'm illustrating here a 96 well plate, which raises the question of scale. In this case, in vitro gametogenesis can produce gametes on a scale that is obviously infeasible in vivo. We might retrieve 10, 12, 14 eggs, let's say, in a conventional IVF cycle. If we were to resort to IVG, we will likely have multiple, in fact, unlimited supply of 96 wells containing the oocytes or the sperm of a given individual. That is a difficult issue to wrap one's arms around. And so scale will be an issue. There will be questions of choice, of course, as to how one wishes to proceed with all of these germ cells. And what, if anything, is to be done with the embryos and the large number thereof that could potentially be created. All of which indicates that there'll have to be significant deliberation well before this ever comes to the clinic, independent of FDA regulation. The potential deliberative bodies in the United States that could be entrusted with such a challenging task could be the National Academy of Medicine, perhaps the Presidential Commission for the Study of Bioethical Issues, which currently does not exist and did not exist during the Trump era, but up to that point was continuously present. We, among others, have called upon the Biden administration to reinstate the commission because of its all-important role. And then there is the Hastings Center, which is the premier ethical house in the United States, on par with the United Kingdom's institute, which we mentioned earlier. As you might imagine, legal implications are also going to arise. The scenarios here can be quite wild. For example, there is the possibility of unwitting non-consensual parenthood if the care of these gametes is somehow less than optimal, if they are in some way falling into the wrong hands and in fact fertilized or however they used to create new life, could give rise sometimes to unwitting non-consensual parenthood. Imagine drinking coffee in a restaurant, leaving the coffee table there when you leave, and somebody wiping it off, retrieving a few skin cells and converting those to gametes. I know it sounds far-fetched, almost sounds science fiction, but we have to consider these possibilities and others, which I think will place more challenges on this technology than the science that will bring it along or the FDA, which will regulate it. In a word, before we delve into this area, which may well be inevitable, all kinds of rules and regulations will have to be in place that we can all live with. And one other important element of all of this, which is not just true for in vitro gametogenesis, but it's true for germline editing and for other novel technologies that overwhelm the populace. And that's the notion of public deliberation. In other words, giving the public, the general public, an opportunity to weigh in on the issue. Granted, the public will be overwhelmed, as it always has been, and there might even be significant backlash. That has been true throughout human history, going back to Galileo or even before that. But we need to give the public a chance. And this is known these days as participatory public engagement, a series of fairly formalized techniques that now constitute essentially a scientific discipline in political science primarily. And it's a discipline that's being practiced quite heavily in Europe, but has not really entered the United States in any major way. Some of the state affairs in the state of Oregon, which has always been ahead of the curve, now involve public deliberation. But for the most part, this will be news to the United States, but it is essential. What we don't want is something along the lines of the so-called Asilomar Conference on Recombinant DNA, which took place in 1975. It was understandable as to how it transpired. That's the way things were done back in 1975. But the problem was, it was experts only and by invitation. The public wasn't there. And so this was not a place for public participation. In fact, not long after that conference, Senator Kennedy, speaking at the Harvard School of Public Health, said that when science develops techniques that fundamentally change society, society has the right to determine how the technique is to be used, whether it should be developed in the first place, and if so, under what constraints. The National Academy of Medicine issued a report in 1995 titled Society's Choices, which dealt with this very issue. And in 2008, another report titled Public Participation, in this case, in Environmental Assessment and Decision-Making. The key statement from that report was that public participation is intrinsic to democratic governance. One other significant speaker for this requirement is Sheila Jasanoff from Harvard, who in her 2012 book, Science and Public Reason, stated that the issue is no longer whether the public should participate, but the question is more how. And the how is, as I said, increasingly being resolved. Technologies are being developed. And so we no longer have an excuse, if you will, to skip public participation because it's for one reason or another not doable. The United Kingdom is a tad ahead of us on this. For example, they evaluated genetic technologies through public dialogue and opinion process back in 2018. And in a report of the Nuffield Council in 2018, a statement was made that establishment of a separate body independent of government, which would produce understanding of public interest through promotion of public debate, is in fact important, if not essential. We do not have such a body in the United States. We called for the establishment of such. For now, it's likely going to be one of the deliberative bodies I mentioned earlier, either the National Academy, the Bioethical Council, or the Hastings Center. Which brings us full circle to where we started. And it places in vitro derived gametes on our collective human horizon. Nobody can tell when this will come to pass, but we have experienced this many times before. A leading paper sees press, the New York Times or the Washington Post carry op-eds on the subject matter, and then we wake up to the issue and start playing catch up. The idea this time around is to get ahead of the game and to see if we can anticipate what needs to be anticipated, and so that if and when this becomes a clinical reality, it proceeds in a manner which we all feel at least reasonably comfortable with, that is regulated and well thought out, as opposed to a spilling effect that will get out of control. So for now, all I can say is stay tuned, but be prepared. Not sure when, but it's likely coming. So thank you very much for your attention.